Hi everybody, this is lecture 35. We only have this lecture and then two more. This is our last week of class. We're continuing our discussion of section 9.3 in Stewart, which is polar coordinates. You'll have questions about this in recitation tomorrow. All right, first thing I want to do is I want to revisit an example that I made a mistake on Friday. I went really fast. Now I'm going to revisit this with slightly different numbers. So meeting part one is going to be more plotting or more sketching. So example one. Sketch the curve r equals 9 cos 2 theta. All right. Now, so let's start by graphing r versus theta. So somebody tell me something about the curve 9 cos 2 theta. Kinsey?
It's bounded between positive and negative 9.
So the amplitude is 9. What else about it? Somebody tell me its period. Jace?
It's shorter. So it'll, from 0 to 2 pi, it'll cross the arrow lines.
That's what cosine of pi would do. What effect does the 2 theta have on the graph? It shrinks it horizontally. So the period is half as long as it would have been originally. So this is going to be a graph that goes up as high as 9 and down as low as negative 9. And the period being 2 pi for the regular cosine graph, this is going to be period of pi. So at pi, so it's going to do this. So it's going to start at 9, go down as low as negative 9, halfway to pi, and then go back up to 9 at pi. So it seems like that's all we need to make the graph. Well, the thing is, we're supposed to sketch this curve in the x, y plane. We've got a graph of r versus theta here. We don't know what's going to happen in the x, y plane. So this is r in the vertical axis and theta. So we need, remember, we're going to let our angles, on Friday I had a red and a green end for the ruler. Here I'm using red and, okay. On the chalkboard, green doesn't show up well, so I'm going to use yellow. For the negative axis, I'd like to use yellow. I don't have a yellow highlighter, so this is supposed to be red for the positive axis and yellow for the negative axis. So we're supposed to be sweeping these angles around from 0 to 2 pi and making a graph. So we need instructions all the way out to 2 pi. Even though our R graph is periodic with period pi, we still need to go farther. So this graph is going to come back down and cross. Do this. Furthermore, remember on Friday when I was making those graphs, in the xy plane, it's handy to start the graph at a place where you know r is 0. So I'm going to continue this graph. What's this horizontal axis intercept? What's the theta coordinate here? Yeah. No. This one here is pi over 4. So negative pi over 4. Now, furthermore, remember from Friday's class, it was useful to color these regions of this graph. The regions that are above the axis where r is positive, I colored red. And the regions that are below the axis, on Friday, I colored green. But green doesn't show up very well on the chalkboard, so I'm going to color these yellow. Okay, so here we go. We're going to graph this. We're going to make the xy plane. Now, a couple things. We know that at odd multiples of pi over 4, r is 0. So this is 3 pi over 4, and so forth. 5 pi over 4, 7 pi over 4. So we might as well put those angles in. The other thing is r goes out as far as 9. So we might as well put in a circle of radius 9. Oops, I should have made that dotted. This is meant to be a guideline. So this is the xy, or xy plane, not the r theta plane. Okay, so remember what we did on Friday. Think of what this is telling us. As the angle sweeps from negative pi over 4 to pi over 4, r starts at 0, goes out as far as 9, comes back to 0. So how does that look? Well, starting at an angle of negative pi over 4, that's the positive x-axis, the red axis. As I sweep the angle from negative pi over 4 to pi over 4, r starts at 0, goes out as big as 9, and then comes back to 0. So this is going to look like the following. So that's what I get from this first lobe. Okay, the second lobe, here, from pi over 4 to 3 pi over 4, r goes out to negative 9 and back to 0. So from pi over 4 to 3 pi over 4, r starts at 0 and goes out to negative 9 down here and back to 0. So my second lobe is actually a yellow lobe, and it's a back lobe. This looks like an angle of negative pi over 2, but it's actually an angle of pi over 2 with a negative r value. And then this third lobe is when the angle sweeps from 3 pi over 4 to 5 pi over 4. So when the angle sweeps from here to here, r starts at 0, goes out as far as 9, comes back to 0. So r starts at 0, goes out as far as 9, comes back to 0. And similarly, I get a back lobe here. So there we go. Example 2. This is what I screwed up on Friday. Didn't make a big screw up. I'm going to have r squared equals 9 cos 2 theta. Okay, well, first thing we're going to do is we're going to graph r versus theta. Now, how high does this graph get? And how low does it get? Marcy?
3.
3. How low does it get?
-3.
Yeah, which is something I didn't say on Friday. So let's look at the right side of the equation. Well, for instance, at theta equals 0, the right side is cosine of 2, it's 9 cosine of 2 times 0. So that's 9 times 1, that's 9. The left side is r squared. So we have this equation, r squared equals 9. So what's r?
Plus or minus 3?
Excellent. That's what I screwed up on Friday. R equals plus or minus 3, as Allison said. So notice that r and theta are related by an equation, but r is not a function of theta. So I would call this a polar equation. Over here, r is a function of theta. So this whole first part of the graph over here, where I had these positive r values going up as high as 9, well, I'm going to have positive r values going up as high as 3 in this case. And the horizontal axis intercept is at pi over 4 and at negative pi over 4. But simultaneously, there are values going down to negative 3. I didn't do this on Friday. Okay, now let's think about the next time interval from pi over 4 to 3 pi over 4. So for instance, including at pi over 2. Well, so at theta equals pi over 2, let's see, the right side is 9 times the cosine of 2 times pi over 2. So that's 9 times cos pi. That's 9 times negative 1. So that's negative 9. The left side is the equation is r squared. So I get r squared equals negative 9. All right, so somebody tell me what are the solutions to that equation? Trent, there are no solutions. So in this part of the graph, I took this graph, I shrunk it vertically, and I added a mirror image on the underside. But on this part of the graph, there are no solutions, so there's a gap. And then from 3 pi over 4 to 5 pi over 4, well, we're back to having a lobe that goes up to 3 and back down to 0, and also a negative lobe. But from 5 pi over 4 to 7 pi over 4, no solution again. And finally, the last bit over there, we have this kind of thing going on. So let's graph this. This is a pretty cool example. Okay, pretty much all examples are cool. So we need to make x, y axes. And our guide, instead of being a dotted circle out at 9, we're going to have a dotted circle at 3. And our important angles are still pi over 4, 5 pi over 4, 3 pi over 4, 7 pi over 4. Okay. Now, as the angle sweeps from negative pi over 4 to pi over 4, my red R values go from 0 to 3 and back to 0, while at the same time my yellow R values go from 0 to negative 3 and back to 0. So here's my angle sweeping from negative pi over 4 to pi over 4. My red R values are going from 0 out as far as 3 and back to 0. So I'm going to get this red lobe. But at the same time, I'm going to get this other stuff going on. This yellow data, that's on the back ray. So here's my angle of negative pi over 4 as it sweeps from the angle from negative pi over 4 to pi over 4. Out here on the yellow end of the axis, my R goes from 0 out to negative 3 and back to 0. So I'm going to have this going on simultaneously. Those both have 1s in them. Now there's a gap in time from pi over 4 to 3 pi over 4. So as my angle sweeps from here to here, nothing happens. There are no R values. I didn't really highlight that there is a dot at the center. And then fun stuff starts happening again at 3 pi over 4. So when the angle gets to 3 pi over 4, again, here's the red end of the number line. As it sweeps from 3 pi over 4 to 5 pi over 4, the red data goes from 0 out to 3 and back to 0. Meanwhile, the yellow data on the back end of that number line, that's the yellow end of the number line, goes from 0 out to negative 3 and back to 0. So I have this. Laid right on top of that yellow lobe is a red lobe, which is the lobe during that second time interval. And laid right on top of that red lobe is a yellow lobe out here. So this should have said 1 and 1. This first thing should have been during the first time interval, there's some stuff happening with the red data and the yellow data. They're both here. A red one and yellow one, and then red 2 and yellow 2. So this is what I missed. On Friday, I just erased the bottom part of this graph and I adjusted the height. But I neglected the fact that a bottom part of the graph shows up. This is not the graph of a function. It's a graph of a polar equation. It's a graph of this equation. So that's pretty cool. Let me quickly, Gabriel, you could pause that if you want. Ready to resume, Gabriel. Meeting part 2, a puzzler. Show that R equals 3 sine theta plus 4 cos theta is a circle. Well, you know, we've seen on Friday, we plotted R equals 2 sine theta. I think that was it. Was that the example? Anybody have notes from Friday? Oh, I do. What's our example on Friday?
We did do 3 sine theta.
3 sine theta. Okay. And that was this kind of thing. It was a circle up here. And that's because when theta is 0, R is 0. But when theta gets as big as pi over 2, R is 3. So this is r theta equals 3 at time pi over 2. And let's think about r equals 4 cos theta. What would that look like? Well, when theta is 0, cos theta is its full value of 1. So this is actually going to be a circle that's hanging out to the right. So this is an r of 4, which happens at theta equals 0. And when theta gets as big as pi over 2, then the r is shrunk down to 0. So each of these things separately is a circle pointing different directions. But why should their sum be a circle? Who remembers this? 3 sine theta plus 4 cos theta. So a sine graph is an example of a sinusoid. A cosine graph is also an example of a sinusoid. So there's a whole family of sinusoids, not just those two. So a cosine graph you can think about as, well, it's a cosine graph, but it's also what you get if you shift the sine graph. So if you shift the sine graph left and right, you get the cosine graph, and at every point along the way, those are all sinusoids. That shifting is what's called, remember the name? Phase shift. You shift the phase of a sinusoid, you just get another sinusoid with a different phase shift. So anybody remember how to rewrite this as a single sinusoid? Well, it's over there on the sideboard. Remember from high school? You learned this. Hey, in the last few years watching British detective shows, I realized that the words shaking your head and nodding your head mean different things. I was watching somebody recording the goings-on of an interview with this suspect. And they were saying the suspect is shaking his head, suspect is nodding his head. So I'd never really paid attention to the difference between those two words. Which is the one where your head goes up and down? Nodding. Okay, on the count of 3, everybody nod your head. Yes, you all learned this in high school. You did. Okay, now, nod your head again. Yes, you've all forgotten this, but still, this is still true. While you've forgotten this, this went on being true. So this is going to be, well, let's see, I got to take the square root of 3 squared plus 4 squared, and then I have to do sine of theta plus tan inverse of 4/3. Now, this direction is just memorization. I didn't remember this. I had to get help. But you can always check. Once you have this, you can use this angle addition formula to go back. You can plug this into this formula, and it really does get you back there. Okay, for the grand prize, what's square root of 3 squared plus 4 squared? Quick. 5. Oh, man. Kinsey gets the prize. So 5 sine of theta plus tan inverse of 4/3. So that's a sinusoid. It makes sense that that's going to be a circle, but let's graph it. What? Well, that was a mistake over here. I think. Right. Because, how do I know that? If you have the graph of cosine, in that case, b is 1 and a is 0. How do you get the graph of cosine from the graph of sine? You move it to the left. Now that means that cosine of theta is sine of theta plus pi over 2. It moves the graph to the left, pi over 2 units. Okay, now let's graph this. So let's graph R. So this is R versus theta. Okay, well, if that were just sine of theta, what would be the most convenient beginning and ending of the graph? Well, it would be from 0 to 2 pi. But this has the effect of moving the graph to the left a bit. So instead of starting the graph at theta equals 0, I'm going to start it over here a little bit, because that's the phase shift. So instead of starting it at 0, I'm starting it at minus tan inverse of 4/3. The phase shift is tan inverse of 4/3, but it's to the left, so the coordinate of this is minus tan inverse of 4/3. So instead of being 2 pi, this is 2 pi minus sine, 2 pi would be here, sorry. This would be 2 pi on a sine graph, but it's 2 pi minus tan inverse of 4/3. And instead of being pi, this is pi minus tan inverse of 4/3. Okay, well, let's do our usual trick. Let's color this red, let's color this yellow, and let's get to work plotting this. Well, convenient angles. At this angle, and at that angle, and at that angle, R is 0. So instead of the angle being 0, it's 0 minus a bit. So this much is tan inverse of 4/3. So instead of thinking about my angle sweeping from 0 to pi to get that circle, I'm going to think about my angle sweeping from negative tan inverse of 4/3 to pi minus that angle. So as my angle sweeps from that angle to that angle, my values of R go from 0 up as high as 5 and back down to 0. So I need to have a guide circle. This is circle out here at 5. And so my R starts at 0, goes as big as 5 when it's halfway there, and back down to 0. Isn't that a great circle? You should all be nodding your heads. Yes. There we go. So this is going to be R equals 5, R theta equals 5, and the angle is going to be, well, not pi over 2, it's going to be pi over 2 minus tan inverse of 4/3. And then what happens for the next chunk of time? Well, we get our yellow, or as the angle sweeps from that angle on around back to the start. It turns out my red and green pen were better. So the angle continues sweeping around. The R values go negative, out to negative 5 and back up. So the R values are going to be on this green pen or yellow pen, going out as far as negative 5 and back down. So that means that superimposed on that is going to be this. So there's the red lobe gives us that 1, the yellow lobe gives us that 2, and there's our circle. Now let's think about the center of this circle. the r value here is 5, but what about the center? Now, if this is alpha, then that means that if I draw a right angle to this line, it goes through that point, and that means that's a right angle, and this is also alpha. It's because alpha plus this little angle here gives me 90. So alpha plus that little angle gives me 90 also. Okay, so this is alpha, and the point that we're interested in is here, and that's going to have r, this is going to be 5/2 is the hypotenuse. So that's the point we're interested in. We're interested in the x, y coordinates of this point. So this is alpha. And so the x coordinate, well, x over the hypotenuse is sine alpha. So that means that x is going to be 5/2 times the sine of alpha. But what's that? That's 5/2 times the sine of tan inverse of 4/3. All right, we got to figure that out. So here's 4, and here's 3, and here's alpha. Alpha equals tan inverse of 4/3. So sine of that, sine of alpha, is going to be sine of tan inverse of 4/3. Well, what is the sine of alpha? Well, what's the hypotenuse here? The hypotenuse here is 5. So the sine of alpha is going to be 4/5. So this is going to be 5/2 times 4/5. So that's going to be 2. That's the x coordinate of that point. Now what about y? Y over 5/2 is going to be cos alpha. So y is going to be 5/2 cos of tan inverse of 4/3. Well, cos of that angle is 3/5. So that's going to be 5/2 times 3/5. So that's 3/2. So the center is at xy equals 2, 3/2. Isn't that cool? Yes, that's cool. So it's a circle of radius 5/2. But I'm going to use capital R for that radius because that's different from our little r. The radius is 5/2. So again, we know it's a circle shape because it's a sinusoid. When you plot a sinusoid, when you plot a polar curve whose polar equation is a sinusoid, you get a circle. It's just, it may be beaming and pointing in some different way, if a circle can point, but you get the idea. So that was method 1. Method 2, so method 1 was by plotting, and I think it's cool. So I guess I didn't say that. Method 1, graph it. So at that heading, that's what we just did. We graphed that, and we figured out that it's a circle. Method 2 brings us back to last week. Use algebra. Now remember, from polar coordinates, we always have this being true. If we have theta and we have r, and this is x and y, from this picture we get a couple of things. We get x squared plus y squared is always equal to r squared, and we get that x equals r cos theta, and we get that y equals r sine theta. So I'm going to do some trickery just using algebra, which is going to get us to the same result. A circle of radius 5/2 centered at those wacky coordinates. So we're going to compute x squared plus y squared. I did this last week for a different example. So we just simply write down x squared plus y squared. Okay, then we use this fact, x squared plus y squared equals r squared. That's always true. And then we do a trick. I'm going to write this as r times r. How did I know to do that? I didn't. It's a trick. I figured it out because I realized, oh, you can do this because I saw somebody else do something similar, and I had to figure out what they did, and I realized what they really did is they just separated that. Now, I'm going to use this formula for one of those r's. So that's another trick. I'm going to use that formula to rewrite one of the r's, but not both of them. So 3 sine theta plus 4 cos theta. So what this is the definition of r. Or this is the formula for r. Okay, well, another trick. I'm going to distribute the r's. That's not really a trick, because this is going to be r times 3 cos theta plus r times 4 sine, r times 3 sine theta plus r times 4 cos theta. So I just distributed the r. Now I'm going to do a trick. I'm going to swap the order. Instead of r times 3, I'm going to have 3 times r sine theta. And I'm going to have, instead of r times 4, I'm going to have 4 times r cos theta. Now you realize that what we've got here is y. And what we've got here is x. So this is 3y plus 4x. Okay, so now we've arrived at an equation that says x squared plus y squared equals 3y plus 4x. Let's subtract that stuff from both sides. So I get x squared minus 4x plus y squared minus 3y equals 0. Now let's complete the square. Okay, what would I like to have here? I'd like to have half of this coefficient squared. So half of 4 is negative 2. Square it, I get plus 4. I'd really like to have a plus 4 there. So I'm just going to do it. X squared minus 4x plus 4. And over here, I'd really like to have something here. I'd like to have half of that coefficient squared. Okay, half that coefficient is negative 3/2. Square that, I get 9/4. I'd really like to have a 9/4 there. So I'm just going to put one there. Now I can't just do that on one side of the equation without also doing it on the other side of the equation. So I have to add 4 and I have to add 9/4 on the right side of the equation. So the reason I put these in here is because I've created perfect squares. This is x minus 2 quantity squared. And this is y minus 3/2 quantity squared. And what's this? This is 16/4 plus 9/4. That's 25/4. Okay, so that's a circle centered at 2, 3 halves with radius 5 halves. So it's centered at, let's remind the reader, this is xy equals 2, 3 halves. And with radius, capital R equals 5 halves. So it's the same result. So pretty cool. Very different way of getting to the same result. And they're both instructive. Meeting part 3 is tangents. Tangents to polar curves. So, given a polar curve and I'm going to say polar function r of theta, the goal, find the slope of the line in the xy plane that's tangent to the curve at time theta. So the idea is we have some kind of wacky thing going on, and this is r comma theta, but this is the xy plane, and so this is also xy, and we're interested in the slope of this line. M is dy dx. Well, let's figure this out. Well, so let's get formula for dy dx. And I should say this is dy dx at theta, at time theta. So let's just get dy dx by itself. Well, dy dx we can get at by doing this. We do dy d theta divided by dx d theta. And so that means we have to take the derivative of r sine theta and divide it by the derivative of r cos theta. Now remember, both of these things depend on theta. So r is a function of theta. So this is going to be, using the product rule, r prime times sine theta plus r cos theta. I had to use the product rule. I had to take the derivative of the first times the second plus the first times the derivative of the second. Now on the bottom I'm going to have r prime cos theta, and then I have to have the first times the derivative of the second. But the derivative of cos theta is minus sine theta. So I'm going to have a minus in the bottom. So example, find the slope. Now, I screwed this up in the first class. I hope I don't screw it up again. Well, maybe you can help me figure out where I went wrong. Find the slope of the line tangent to, what was our first graph? Was it, well, let's just do a circle. Let's do 5 cos theta at theta equals, well, let's figure that out. Let's figure out where we want to do a theta. We know this is going to be a circle, and it's going to have its full r value when theta is 0. So this is going to go out as far as 5, and it's going to be a circle like this. So this is at theta equals 0, and at theta equals pi. Two pi. And no, it's actually pi and 2 pi, because this goes around twice. Remember, from 0 to pi, from angle of 0 to an angle of pi over 2, the r starts at 5, goes down to 0. And from pi over 2 to pi, r goes negative. So the circle goes around twice. So what would be an interesting place to get the slope? Let's do this. What do we expect the slope to be here? We expect the slope to be -1. Now, what angle is this? This is at theta equals pi over 4. So let's do that. Find the slope of this angle, slope of that tangent line at an angle of pi over 4. So again, hopefully I won't screw this up like I did in the first class. It's a good thing you paid extra for the premium class. Okay, so in our case, dy dx is going to be, so this is our r, and r prime is going to be -5 sine theta. So our dy dx is going to be -5 sine theta. That's our r prime. I got to multiply that by sine theta. And then I got to multiply, and then I got to add r cos theta. Well, so I have 5 cos theta, that's our r, and I got to multiply it by cos theta. On bottom, I'm going to have -5 sine theta times cos theta. And then I'm going to have minus a 5 cos theta times sine theta. Wow. I don't know. This isn't looking good. But let's see. When theta is pi over 4, all these sines and cosines are pi over 4. Are 1 over radical 2. So I have -5 times 1 over radical 2 times 1 over radical 2. And then I have +5 times 1 over radical 2 times 1 over radical 2. I don't know. There's a sign going wrong here. So you see what I get in the numerator is 0. Where did I go wrong, everybody? Help me out here. So in the bottom, I'm going to have -5 times 1 over radical 2 times 1 over radical 2. plus, minus another 5. So in the bottom, I get minus 5 halves minus another 5 halves, so I get minus 5. Now in the top, I really want to get a plus 5. Why am I not getting a plus 5? Well, I'm going to put a big question mark here. So to win the big math prize, figure out where I went wrong. Where did I go wrong? And the answer is not by going into mathematics, although my family would say that. Okay, let's do the last example. Oh, perfect. We have just enough time. This is example 5. So again, that last example. Oh, right. Hello. This is time 0. This is time pi over 2. Time pi over 4 is here. Hello, everybody awake? So we would expect the slope to be 0 at theta equals pi over 4. I get the prize. Woohoo! So the slope was 0, just as I expected. Zero over minus 5, so I get 0. Yes. All right, the last example, I promise, is short. Find the slope of the polar curve r equals 1 over theta at theta equals pi. Now the cool thing about this, what's the radius when theta is 0? Undefined. What's the radius when theta is really big? 0. What's the radius when theta is really small, close to 0? The radius is big. So this is actually a spiral. It's very cool. So at time 0, the radius is not defined, but for very small positive angles, the radius is giant. And so what this does, it's amazing. So there's no point here, and there's no point here. Coming in from time 0, from theta equals 0, something like that. Okay, so I got to do one of these things. My r is 1 over theta. So my r prime is minus 1 over theta squared. So my dy dx is going to be minus 1 over theta squared sine theta plus 1 over theta cos theta divided by minus 1 over theta squared sine theta, or that's cos theta, minus 1 over theta sine theta. Okay, but our theta is pi. When theta equals pi, well, sine theta is 0. Cos theta is negative 1, so I have 1 over pi times minus 1. Let's look at the denominator. at theta equals pi, cos theta is minus 1. So I have minus 1 over pi squared minus 1. And then, okay, at time pi, theta, a sine of pi is 0, so this is 0. So I get minus 1 over pi divided by plus 1 over pi squared. So this is miraculously a beautiful result, minus pi. There we go. So at time pi, we're about here. M equals minus pi. At time, r theta would be 1 over pi, comma pi. The angle is pi. The radius is 1 over pi. There we go. So two very different kinds of calculations of a tangent line slope. Now remember, this is an r theta. This angle is pi for the polar coordinates of this. I'm sorry, not the polar coordinates. The r theta coordinates are 1 over pi, comma pi. The point here does not have an angle in the xy plane of pi. This occurs at time theta equals pi. But you'll see that this point is actually somewhere in the upper half plane. So this is the xy plane. All right, thanks everybody. I'll see you on Wednesday.